So welcome back to today is the 17th lecture of the 4th week. So in the last lecture we talked about the basic configuration of AFM, right? And we talked about how the AFM tip could be modified in multiple ways based on the kind of substrate, kind of sample we are dealing with. So let's get to today's lecture, which is lecture 17, and what we'll be doing is AFM for biosensing. This will be the part 2 of today's lecture. So to start off with, the first configuration is the tip sample interaction types. What are the different kind of interactions which are possible? The tip sample interaction typically falls onto 3 categories. First is the contact force. When we talk about a contact force, that means, so for example, you have the tip, you are approaching the tip and you are hitting on the surface. What is the force of contact? At what force you are hitting on the surface? Because that will decide that what is the nature of the substrate, right? Will it sink? Will it go up? So on and so forth, right? Second thing is controlled amplitude, frequency or phase of the cantilever resonance oscillation. That means here you are controlling the amplitude and the frequency or phase of the cantilever's resonance oscillation. That means, say for example, the cantilever hits on a substrate. So the cantilever used the tip of the cantilever, if you just visualize it, it starts to vibrate. So it generates a resonance frequency. So for example, if here you have the cantilever which is tapping the surface at a particular frequency, upon hitting it may frequency may change. Similarly, third mode is the controlled off resonance tapping force. Here what you are doing is you are actually introducing a tapping force and you are seeing the change in that force while your tip is moving across the surface. So these are the basic 3 fundamentals. And if we look at in a diagrammatic fashion, tip sample interaction and a contact mode, what contact mode is all about. So this is what the contact mode looks like. Okay, so its principle is that probe tip is not oscillated but constant contacted with a sample surface and is operated in a repulsive regime. The cantilever tip moves up and down to accommodate the surface topography, which can be measured by either the cantilever deflection or using a feedback loop to keep the cantilever at constant position. So you are moving like this, cantilever is moving like this. You have to be very careful, it can even break down the tip. Typical application, non-fragile samples such as mineral particles and graphene films. These are hard enough, but you have to be very careful that you are not damaging the tip. So this is the contact mode. Okay. Next mode is non-contact mode. Second one. Non-contact mode is much more tricky. The cantilever tip is kept away from the substrate. You see, the tip is not touching the substrate and oscillate the tip with small amplitude near or at least its resonance frequency. Tip surface interaction induces oscillation changes but is maintained by a feedback loop system by adjusting the average tip to sample distance, which can be further used for topography imaging. This one is a very classic one where you are maintaining a finite distance all the time. As it mentioned, if you follow this particular part, that adjusting the average tip to sample distance, which can be further used for topography imaging. So you are maintaining a fixed distance. Okay, so let's again go through it. The cantilever tip is kept away from the substrate, so it is not touching the substrate. No contact, as it says, no touching, and oscillate the tip with a small amplitude near or at its resonance frequency. Okay, So you are basically oscillating the tip, and tip surface interaction induces oscillation changes but is maintained by a feedback loop. Okay, so this oscillation frequency is being monitored by the detector. This is the second mode, and this is being used for metals, semiconductor, polymers and biological material. Especially this is the part which is of importance to us, because in that situation, when it is a non-contact mode, you are not touching the sample. So your tip is free, because mind it, if you touch the sample, if you go back, say for example, you are looking at some pathogen, and when you are hitting the pathogen, there is every possibility that tip may break the pathogen surface, and that is something you do not want, because it could lead to contamination. So for such situation, and these are the choices you as a investigator will have to make, that what kind of probe you want to use, and that you can only do when you understand what is the capacity and capability of each one of these probes. So in that situation, for biological samples, you will rather prefer a non-contact mode, where you are not touching the sample, and yet you could gather maximum information out of it. Third one is the intermittent mode. This is somewhere in between. The cantilever tip oscillates with a large amplitude and is kept away from the substrate surface and intermittently contact with the sample surface. This is somewhere in between a contact and non-contact mode. Okay, the tip surface interaction induces oscillation changes, but a feedback system is used to adjust the cantilever height to maintain a preset oscillation amplitude. Most popular mode is soft samples such as hydrophilic polymer or biological samples. So this is something which is a very interesting thing. This is a situation where, say for example, sample, say you remember in the first class I was telling you the sample deformities, you can really pick up the deformities using intermittent mode. So while you are maintaining a reasonably constant distance between the substrate and the tip, but there are times when you are, as it says, kept away from the substrate surface and intermittently contact with the sample surface. The tip surface interaction induces oscillation changes, but a feedback system is used to adjust the cantilever height to maintain a preset oscillation amplitude. This part is very important. So these are the three different modes. So you could see that it is the intermittent mode and the non-contact mode, which are favored for most of the soft matters and biological samples. Now I move to a third form. So if you go back, so using these modes, we can, if I go back to the previous lecture, so I have covered this. Now I am in this one, which is your scattering, scanning, near field optical microscopy, SNOM, or nanospectroscopy in chemical identification. So I'm that part C. Now let's get back to part C. What does this say? As the short form SNOM is scattering, scanning, near field optical microscopy. Scattering, this is the small s, see actually this is small s, S N O M. In short, you will see something like SNOM, it is written in the literature, for nanospectroscopy in chemical identification. Now, even before I get into this, one important thing which I wish to highlight, and most likely next week I will go through a very basic tutorial of the role of or interaction of light and matter. Okay. So when we are talking about putting a probe like this on a substrate, you're basically, there is every possibility that you are kind of disturbing some of the atoms and you are creating atomic vibrations. Apart from it, if you shine a laser onto the sample, you also can create such atomic vibrations, which is the basis of any form of light. If you give, that is the form of the spectroscopy. Now think of a situation where if somebody wants to couple spectroscopy with AFM. Okay, so how that works? So here you have the AFM tip, as you could see, and here you have the laser beam falling. So focus the laser light onto a sharp AFM tip. This is step one. You see, this is the incoming laser beam. Illuminate the tip to create a strong near field nano focus at the apex. So that's what is happening here. Point. So it is illuminated enough in the tip to create a strong near field nano focus at the apex. Third thing, what is happening, which is exactly here, this event, which is nanofocus probes optical properties of the sample below the tip, modifying the tip scattered light. So what we are looking at is the scattered light. So when we are talking about scattered light, realize there are few simple things which could happen. Say for example, this is a sample and there is a beam of light falling into it. Some of the light will reflect, some will get scattered, some will pass through it. This is the simple basic things which could happen. The one which will pass through it, depending on the atomic packaging, wherever there will be gap, it will pass through. What we call, it will get refracted, it will get bent, but it will pass through, right? Some of it will hit directly onto the atom and may get reflected, and some of it will get scattered like this all over the place. But all these three pieces of information could be utilized for spectroscopic purpose. None of these things go waste. There is few more other stuff which does happen, which are very interesting. Some of the light even may get absorbed by the material, and at times some of the light creates vibration within the atoms. So what I said, again let me repeat, when you are shining light, either the part of the light will get reflected, straightforward, part of the light will get scattered around, part of the light will pass through by bending and everything, hit, right? Part of the light will get absorbed by the material, and part of the light will, the energy of the light will create vibrations within. And all these 5 different things could be utilized for spectroscopic analysis. And if you could couple this with AFM, it could do wonder. And that's exactly what we are going to discuss on this point 4, is what is exactly happening out here at this particular point. If point 3, let me now put it together. A nanofocus probe optical properties of the sample below the tip, modifying the tip scattered light. So you are now quantifying the scattered light. All the optical interferometric detection recovers both amplitude and phase of the tip scattered light, delivering complete information about the sample's complex optical properties, absorption and reflectivity. Spatial resolution down to 5 nanometer depending on the tip sharpness. So this is where now you have both pieces of information which are coming. And by the way, these are all compatible, and we'll talk about it with IR, Raman and all other different light forms. So if you look at the next slide, that will give you a real time situation what exactly happened when we talk about the infrared scattering. So I told you that there is a scattering which is happening. So if I go back to the previous lecture, just taking the liberty to show you. There was a picture. You saw this scattering which is happening. This is exactly what we are going to now talk about. What is that whole scattering is all about? Now, if you look at this whole picture, here you have incident beam which is falling, and what you see is the scattered light. The incident infrared light is focused under the AFM tip apex, and the scattered light carrying the optical properties of the sample is collected. Okay, and here is the compound, which is just for the understanding sake. Okay. The localized light and matter interaction under AFM tip can provide a spatial resolution. So, say for example, if you have a surface, it has multiple different kind of compounds or functional groups which are there. Now, your tip is moving. It will be able to map at what part of your sample which functional group is present. Where you have a hydroxyl group, where you have an amine group, where you have an imido, azo, where there is a sulfur, so on and so forth. You can figure it out, right? So, now look at, so here you have the AFM probe, here you have the interferometer which is taking the incident and the scattered IR light. With interferometric detection, both amplitude and phase images of a sample at a given wavelength can be figured out. By scanning across the sample while detecting the elastically scattered light, the optical response of the sample is imaged. So, this is the overall assembly, and if you look at it, a sub 10 nanometer resolution optical chemical imaging is feasible with this technique. Nano FTIR spectroscopy is being done, where you are parallelly detecting the chemical nature of the compound which is under the investigation. Okay, and overall, this is how this whole assembly of AFM can be coupled with this particular system. Now, there is another way of looking at it. This is one side. So, where you had the scattering, you remember I told you that you write S, that is a scattering, SNOM. But what is just SNOM? Now, I'll talk about that. Scanning near field optic microscopy, okay, SNOM. Now, there is another form of cantilever. You remember I mentioned that, say for example, you have a cantilever tip like this, and you shine a laser from like this, and the laser passes through the tip. What will happen? And this is exactly what is being shown here. There is an excitational laser which is coming like this, falling on it, and it is passing through it. So, there is a near field. In a scanning near field optical microscopy, the excitation laser is focused through an aperture with a diameter smaller than the excitation wavelength, resulting in an evanescent field or a near field on the far side of the aperture. Here you create a near field. Okay. Once again, let me repeat. In a scanning near field optical microscopy, the excitation laser light is focused through an aperture with a diameter smaller than the excitation wavelength, resulting in an evanescent field or near field on the far side of the aperture. When the sample is scanned at a small distance below the aperture, the optical resolution of the transmitted or reflected light is limited only by the diameter of the aperture. The optical resolution attainable in this range is 60 to 100 nanometer, and the optical image is generated by scanning the sample surface point by point and line by line. So, this is another very advanced form of SNOM, where instead of scattered light, you are doing it a slightly different way. Now, we will talk about this now in further detail in this, where near field Raman imaging is being done. I will come to Raman spectroscopy later, but at this point, so here is your beam, here is your near field is being created, here you have the transmitted light going through the sample, and here it is going to the spectrophotometer. Okay, and this is the excitation laser light, and this is the SNOM cantilever tip, and this is the transmitted light. So, previously we talked about the scattered light, right? in the previous example. Now we are talking about the transmitted light, which is directly passing through it. The excitation laser light is focused through the SNOM tip, resulting in a near field, evanescent field on the far side of the aperture. While the sample is moved to a piezo-driven scan stage, the transmitted light is spectroscopically detected point by point and line by line in order to generate a hyperspectral Raman image. The optical resolution of the transmitted light is thereby only limited by a diameter aperture of less than 100 nanometer. Using a beam deflection setup, as in AFM contact mode, it is ensured that the cantilever is always in contact with the sample. In addition to the topography can be recorded simultaneously along with these measurements. This is the very basic principle of the Raman imaging, where you are detecting the vibration and you are identifying the atomic resolution. We will come to the Raman later. At this point, this is the conformation of using a cantilever tip along with the Raman spectroscopy, how you can do it all together in one setup. A further advancement of this is tapping AFM IR, which is even a much more advanced form of it, which is what you are trying to do is you are taking it and you are tapping onto that surface like this. That gives even more additional information, and specifically this is very important when we are looking at a virus surface, because whenever we draw a cell, we draw it like this, but in real life a cell is never like that. Cell has lot of curves and bends and everything, and they are all very soft matter. They are very flexible, they change shape. Okay, so high speed pulse tunable IR laser light is focused onto the sample at a AFM tip location. The laser pulse rate is tuned to match the characteristic AFM cantilever. The AFM tip is oscillated at a resonance frequency in tapping mode and intermittently contact the surface. Again, this is that intermittent, if you remember I mentioned earlier. When the IR wavelength matches the material absorption bands, rapid pulse thermal expansion occurs. This photothermal expansion due to sample absorption causes an increase in the amplitude at an alternate oscillation mode of the cantilever. A local IR spectrum is generated by monitoring the cantilever amplitude as the laser wavelength is swept. High resolution IR images is possible by scanning the AFM probe across the surface and monitoring the cantilever amplitude at a fixed wave number. So you can really go to sub-nanometer resolution of chemical imaging, biological membrane sensitivity, and organic and inorganic samples. This is the kind of power of this particular technique, and in the next class we'll further highlight how these could be taken to the next level. Thank you.